Let's now turn our attention to the implications of space group symmetry on the structures of various types of crystals. In this lecture, we're going to look at ionic and metallic crystals, which often adopt high symmetry structures. And in the next lecture, we're going to look at molecular solids, which usually do the opposite and adopt lower symmetry structures. At the outset, I want to point out an important resource. There are various databases of known crystal structures. These three are probably the most important, and in each of these databases we can find thousands, actually hundreds of thousands of different crystal structures. And when you're trying to figure out the crystal structure of a new compound, it can oftentimes be very useful to look at the patterns of compounds that are already known. We could look at the Cambridge Structural Database, which gives us information about organic crystal structures. And we would see that no less than 95% of all of those crystal structures fall into the orthorhombic, monoclinic, and triclinic crystal systems. What we don't see in these crystals are a lot of higher order rotation axes, fourfold axes, threefold axes, sixfold axes. We're going to come back to those structures in more detail in the next lecture, and we'll learn why that is. If we look at the inorganic structures, which are contained in the ICSD, the Inorganic Crystal Structure Database, we see a much more even distributions across all of the crystal systems. And in fact, the cubic crystal system is actually the most represented among inorganic crystal structures. And then finally, just to say a little bit about proteins, proteins are a little bit in between. So we don't see very many very low symmetry triclinic protein crystal structures. But on the other hand, we also see very few high symmetry cubic crystal structures. And the reasons for that have to do with differences between the way that proteins pack together and the kind of degrees of freedom they keep versus the way that organic molecules pack together. Now, if we were to dive a little bit deeper into the inorganic crystal structures, these 6 space groups are the most common. So we see the P21 upon C monoclinic crystal system is the most common. We'll see when we look at organic crystal structures that there it's even much more common. And that has to do with the way that molecules pack. And of course, even in inorganic chemistry, there are many, many examples of molecular substances. But then we see a couple of cubic crystal systems that are next. And these crystal systems have a lot of symmetry. They have intersecting mirror planes. They have threefold axes on diagonal directions. They have fourfold axes, and they have glide planes. And the reason why we see such high symmetry structures has to do with the kind of forces that favor bonding in metallic and ionic solids. Remember, in metallic solids, we oftentimes want the atoms to pack together closely, and so that tends to lead to highly symmetric structures with mirror planes and rotation axes. The ionic bonding interactions that are operative in ionic crystals also favor highly symmetric structures. And so that's basically why we have so many of these entries. And then we have a variety of other entries here, and these also tend to be high symmetry, but here we see the triclinic case come up, and that probably is largely due to molecular compounds. Okay, so let's talk about representing these structures. To do well in this course, you need to have a software program that can allow you to visualize crystal structures. There are many such software programs out there. These are 3 of the ones that I'm familiar with. They're all quite common. The Vesta software is free. That could be a good choice if you don't have a license for any other software package. But you're going to need to become familiar with how these programs work and make the most of them. Now, if we were to look at the representation of a crystal structure of, let's say, the mineral fluorite, all the information that we need to convey that completely depicts the crystal structure is given in the table above. Right, we have to specify the space group symmetry, here FM3 bar M. We have to specify the dimensions of the unit cell. And since this is a cubic space group, once we specify the length of the edge of the cube, we've given all the information that's needed to specify the unit cell dimensions. And then we have to list each crystallographically independent atom. What do I mean by that? So we have calcium, which sits on Wyckoff site 4A. And one of the calcium atoms in the unit cell has coordinates 0, 0, 0. This calcium right here. The fact that it's Wyckoff site 4A tells us that there are 3 other symmetry equivalent atoms, and those are given at these coordinates. In this particular structure, they happen to be the lattice points of a face-centered cubic lattice. We don't write out the other 3 atoms. It's enough just to say Wyckoff site 4A and give the coordinates of one atom. Then we have the fluoride ion, which is on Wyckoff site 8C. And one of the 8 symmetry equivalent atoms is at Wyckoff site quarter, quarter, quarter. This one right here. And so by writing this, it tells us that there's also 7 other symmetry equivalent atoms that are at these coordinates given here. They're all permutations of 1/4 and 3/4. I guess I should say that it doesn't really matter which one of these we write. We don't have to write 1/4, 1/4, 1/4. We could have written 3/4, 1/4, 1/4, and that would have also been okay. But we are not going to write out all 12 atoms in the unit cell. We only have to write out the positions of the atoms that are unique by symmetry. Now, in representing crystal structures, oftentimes we might choose to draw more than a unit cell. In the structure of calcium fluoride, the tetrahedral coordination of the fluoride ion is pretty evident from just one unit cell, but to see the cubic coordination of the calcium, we have to actually add atoms that are beyond the unit cell boundaries. But of course, that's totally allowed because we can create whatever symmetry equivalent atoms we need to depict the crystal structure. One of the things that's going to be useful in both a forward and a backward direction is calculating the density of a crystal. And we can do this from the crystallographic information because density is an intensive property. That is to say, the density of the atoms in the unit cell must be the same as the density of a crystal that I can pick up with my fingers or with a pair of tweezers. We know that the density is just equal to mass over volume. And if we want the density at the unit cell level, it would be the mass of all of the atoms within the unit cell divided by the unit cell volume. From the multiplicities, we saw that there were 8 calcium ions and 4 fluoride ions in the unit cell. We have this parameter Z, which is the number of formula units per unit cell, and in this crystal structure, Z is equal to 4. There are 4 CaF2 units in the unit cell. So let's calculate first the formula weight. We have the molar mass of calcium plus 2 times the molar mass of fluorine. That gives us 78.08 for the formula weight of calcium fluoride. And then the mass of the atoms inside one unit cell is equal to that number multiplied by Z, 4 formula units per unit cell. And then, we don't have a mole here. We have individual atoms, so you have to divide by Avogadro's number. When we do that, we get about 5.2 times 10 to the minus 22 grams is the mass of the atoms in one unit cell. The volume of the unit cell is pretty easy to calculate. We know the length of the unit cell, 5.46 angstroms, or 5.46 times 10 to the minus 8 centimeters. Let's cube that, and that will give us this volume of the unit cell. And then the density is just the mass divided by the volume, and here that would be 3.19 grams per centimeter cubed. That's the density of a fluoride crystal. Now, when we're doing these density calculations, sometimes we'll encounter unit cells where it's not quite as straightforward to calculate the volume as it is for a cube. And here are some formulas you can use for the unit cell volumes of various shapes of the unit cells. Okay, this class is about using X-ray diffraction, neutron diffraction, electron diffraction, and what we're normally going to be doing is we want to work backward to the crystal structure. Okay, and in those cases, while we're trying to figure out where the atoms are, it's really powerful if we can determine how many atoms there are in the unit cell. What that constitutes is calculating this parameter z, calculating how many formula units there are per unit cell. So we can do that in basically a backwards calculation of the one we just did. Let's start with the relationship for density. And then let's write it as we did previously. The formula weight times z divided by Avogadro's number, that's the mass, divided by the volume of the unit cell. If we rearrange to solve for z, we get this formula. And if you look at this formula, we can get the volume of the cell from a diffraction experiment. So we'll talk about that later in the semester, but using diffraction, we can determine the dimensions of the unit cell. Avogadro's number is just a constant, of course. If we know the composition of our material, we know what the ratio of the different elements are, we can determine the formula weight. And then we're left with the density. And so if we can make an experimental measurement of the macroscopic density, we can use that value to determine z. Let's do an example. Let's say that we did a reaction between one equivalent of zinc oxide and one equivalent of chromium 203. So if the reaction goes to plan, we should make zinc chromium 204. And we do a powder diffraction experiment. We determine that this is a cubic crystal, and the space group is FD3 bar M, and the length of our unit cell edge is 8.327 angstroms. And we were to measure the density and come up with 5.4 grams per centimeter cubed. Knowing this information, what can we say about the structure of this compound? Can we determine where the atoms are in the unit cell? Can we determine which Wyckoff sites are occupied? Can we determine everything up to the bond links? Well, let's see how far we can go with just this limited information. So the first thing we want to do is to calculate z. And so we're going to use the formula we had a couple slides back. First, we need to know the volume of the unit cell. Our cubic unit cell edge is 8.327 angstroms. And if we convert to centimeters and cube that, we get this, 5.77 times 10 to the minus 22 cubic centimeters. The formula weight is 1 times the molar mass of zinc, plus 2 times the molar mass of chromium, plus 4 times the molar mass of oxygen, and that gives us 233.4 grams per mole. And then plugging those values and the density that was measured experimentally into this formula, we come up with z equals 8.04, which is quite close to 8. Right? Z has to be an integer. So we have now established that there are 8 formula units in one unit cell. And so in terms of numbers of atoms, if we go back to our empirical formula of zinc chromium 204, that tells us there are 8 zincs, 16 chromiums, and 32 oxygens in the unit cell. Now that we have that information, let's take a look at the international tables for crystallography and the Wyckoff site multiplicities. So the space group FD3 bar M is a pretty high symmetry space group. And in fact, if we were to put an atom on a general position in this unit cell, the face centering and all of the different point symmetry elements would generate 191 other symmetry equivalent atoms, right? So the multiplicity of the general site is 192. Well, in a unit cell that's only 8 by 8 by 8 angstroms, there's just no way you're going to put 192 atoms in it. So if we look at these site multiplicities, we can see that many of them are too big for the number of atoms that we have in the unit cell. So if we were to start with the zinc, we've determined there's 8 zinc atoms in the unit cell. And unless there's some kind of disorder in the crystal, which is always a possibility, but let's assume that we don't have disorder for this case, then the zinc has to go either on 8A or 8B. These sites have 4 bar 3M, right? That's perfect tetrahedral symmetry. So we're going to put the zinc on one of those sites. We don't know which one, but we know it should be one of them. Then if we look at the chromium, well, the chromium, there's 16 chromiums. So You could get 16 either by putting chromium on 8A and 8B. That would be 16. But we can't do that because one of those sites has zinc, and because all of the coordinates are fixed here, you can only put one kind of atom on that site. So what that tells us is that the chromium must go either to Wyckoff site 16C or 16D. Now we're left only with oxygen, and we know there are 32 oxygens in the unit cell, and by a similar kind of logic, we can't put oxygen on both 16C and 16D because one of those sites has chromium. So it tells us that the oxygen must go to site 32E. And here, while we do have an unknown, those sites are on the threefold axes that go along the body diagonal. So their position is not precisely fixed, just anywhere on that threefold axis, which also has a parallel mirror plane. So we will still have to determine X. But we've made a lot of progress. There's not that many combinations between zinc on 8A or 8B and chromium on 16C or 16D. So we could actually, by trial and error, probably come up with a pretty reasonable crystal structure for this. As it turns out, the crystal structure for this compound is shown here. We do have zinc on Wyckoff site 8A, chromium on 16D, and the oxygen goes on 32E. And that free coordinate, the XXX, X is 0.3815, that fraction of the way through the unit cell. This structure may well look familiar to you. This is the spinel structure, and we have zinc on the tetrahedral sites and chromium on the octahedral sites. One last thing before we leave this, the special positions like 32E, which have variables to them, XXX here, it doesn't mean that we can only put one atom on a 32E site. As long as the atoms don't go on top of each other or too close to each other, we could have multiple atoms on that site. But they would have to have different values of X, different enough that they're not too close to one another. So that's a good thing to keep in mind when we're using this approach to try and figure out crystal structures of compounds. Sometimes it's not very easy to measure the density. If you've got a polycrystalline sample like a powder, you can't really pick up a crystal and measure its dimensions and weigh it. You can't very easily put it in a liquid and see how much volume is displaced. You might be able to use what's called a flotation method of determining the density, where you use liquids of different density and see which one has a density that matches your crystal. But in polycrystalline aggregates, even that's kind of tricky. So it can be useful to use a kind of a heuristic to make a rough estimate of Z. And a couple of ones that are useful are when you're working with organic molecular crystals, we could assume that every atom occupies a volume of 10 cubic angstroms, every atom including the hydrogens. When we're working with, let's say, ionic materials like oxides, we can make an assumption that every oxygen occupies a volume of 20 cubic angstroms, and then the cations just go into the voids between those oxygens. Now, these only give really rough estimates of Z, but sometimes a rough estimate is enough. I mean, we only need to get Z to the nearest integer, and sometimes not even that precise. In the last example, we really just needed to know Z to the nearest multiple of 8. So if we were to see how accurate these heuristics might be, let's just take a look at a handful of oxides that I just basically chose randomly, and I looked up their volumes and their Z parameters. And we can see here, in the compound that we just did, zinc chromium 204, that the unit cell volume divided by those 32 oxygens would give us 18 cubic angstroms per oxygen. And then if we look up and down the list, we'll see that 20 is not a bad estimate, but we do have to acknowledge that there's a bit of spread here. When we have really small cations like aluminum, you can see we can deviate relatively far from that, at least 25% or more. When we have large cations, like in barium bismuth oxide, we can deviate in the other direction just as much, if not more. But at least it gives us a starting point to think about how to determine Z. Because knowing how many atoms are in the unit cell and knowing the space group symmetry, that combination is actually very powerful for high symmetry structures. It's less useful if the symmetry is monoclinic or triclinic and the unit cell is big, because the site occupancies of the Wyckoff sites for those low symmetry structures are pretty small. But we're going to talk about how to deal with those compounds in the next lecture.